energy in systems, heat and thermodynamics. So far, we've tried to simplify as much as possible. Whenever possible, we treated objects like points. We considered a spherical cow, even an athlete or an automobile with sort of as a point. You focus your attention on the center of mass, you watch it move, it obeys Newton's laws, and then, of course, we recognize that the world is more complicated than that. And so we started adding in the complexities. You don't have to always neglect friction. Once you understand the underpinning law of nature, friction is just another force. You can calculate it, you can observe it, and you can add it back into the F side of the F equal ma. If you watch the athlete diving of the high dive, you can watch their center of mass. But you can also recognize that they are doing spins and turns, and you can calculate and understand the rotations around the center of mass, or even the change in the shape of their body, which makes the story even more complicated. Fundamentally, we've been trying to treat objects as though they were as simple as we possibly could. That's why we were able to function historically for so long without worrying about whether atoms are real or not, because we weren't really looking down all the way very often to this microscopic building block level. This is a very, very successful strategy. It has been extraordinarily productive throughout history and continues today. Yeah, this is what is happening in the consultant firm, like the McKinsey, ABM, Bain, whatever. They take a strategy as the scientists do. That is why they are still outstanding under the productive, powerful, practical, right? An astronomer even today can think about the motion of the Earth and understand the seasons and the phases of the Moon, and you don't have to worry about such things as, well, there is a Mount Everest and so it's not really perfect sphere, or we have our atmosphere so it's not really a solid body. It depends on the questions that you are asking. If you are worried about global warming, then you do have to worry about the atmosphere, and that little thin layer can have many important consequences. In this lecture, and basically throughout the rest of the course, I want to make the transition from thinking about the world as simple as possible to recognize that the world is built out of many little tiny atoms. Things, even simple things, are enormously complicated. Even granting this, it turns out that we can make sense of what's going on. It's the last piece of the classical physics story where we accept this reality and look for our consequences, and again try to think about the consequences in as simple as a way as we possibly can, right? This is a field of thermodynamics. That's the name for the branch of physics we are talking about. It belongs to the classical physics. Thermodynamics. Thermo makes you think of temperature. Thermometers and dynamics makes you think about the why questions. Why does one object cool off and another object warm up? Why does that flow the way it does? There are the kind of questions that we want to investigate. When you study the thermodynamics, you begin to recognize that the microscopic internal degree of freedom, the atoms, are very useful. It's quite fruitful to know about their existence. Wow. Thermodynamics goes beyond just descriptions. It's not kinematics. It really is dynamics, and that means we are going to need some fundamental laws to help us to make sense of what's going on. In a certain sense, we can use the fundamental laws that we've already built up and the classical Newtonian laws. We will introduce some laws of thermodynamics There are only a few of them, and they are reformulation that help us to make sense of what's going on in the thermal systems. In the thermal systems and their thermal physics, it's everywhere. It is of enormous practical importance. Just think about your home and insulating it in the winter time and cooling it in the summertime. Then you go in the kitchen and you turn on the stove. You'd like the food to heat up quickly, but not too quickly. You want to measure the fever of the small child. You want to predict the melting of glaciers on the Greenland. Many things in the world rely on the understanding of thermodynamics. It's a lovely field to be wrapping up this course with, because the thermodynamics really does put together all of the big ideas of the classical physics. We will think about F equal ma. We will think about energy principles. We will think about the atomic hypothesis. We will think about statistical mechanics. This idea that microscopic motion can explain the microscopic thermodynamics. And the idea that the microscopic motion can explain microscopic thermodynamics is a lovely and powerful connection. You can talk about thermodynamics without ever talking about atoms. You can put a pot on the stove, heat it up, and make measurements of the temperature as a function of the time, and never talk about atoms. But we are going to think about atoms because although it historically took some time before the atomic hypothesis was forwarded with the pure, straight observation about temperature and heat, in the end, when you do put them together, it makes everything make so much more sense. Thermodynamics begins with energy and energy flow. That is really one of the languages that help us to understand heat and heat phenomenon. When you have a complex, real-world system and any normal object has lots of atoms in it, a pot of water might have a billion water molecules in it. If you ask how I could understand what's going on, the reductionist viewpoint would say, alright, go all the way down, look at the atoms, look at the forces between them, track them. There is an object that starts here. Now it feels a kick, so now it goes that way. That might work, but boy, would that be tough. And nobody has really ever thought about in a practical way understanding a pot of water by going down to the individual water molecules. Instead, and this is really the big idea of thermodynamics and the statistical mechanics, think about averages. Think about the behavior of typical atoms. And don't worry about the details. This is a simplification that's going on in thermodynamics. If you focus on the average, thinking about energy will be definitely help because it gives us a nice, concrete, measurable handle, and then we are going to be able to make sense of what's going on. Think about the insurance company that can make a living very confidently by making predictions about when people are married, when people have babies, when people are sick and how often they are sick, and when they die. It's not so hard to make these predictions on average. It's impossible to make these predictions for individuals. You could never do it. Insurance companies don't try to make a specific guess about you. Instead, they insure many people and they figure everything will wash out. That's very powerful idea and it works very well. Wow. Atoms are much simpler than people, so it's nice. If the insurance company was dealing with something simpler than a human being, they would have an easier job and it become easier and easier as an insurance company insure more and more people. my university had a little bit of trouble a few years ago because we went with a small local medical insurance company, and the fact that they were only ensuring the local community meant that the 1 or 2 freak accidents somebody who has a heart attack much younger than you would have expected and then cost the company a lot of money can have a big impact. Colorado University. No, Denver University? Colorado University, I guess, yeah. When you are averaging over hundreds of millions, let alone millions of billions or billions, then all of a sudden the details of the individuals hardly matter at all. Thermodynamics, the study of understanding of temperature, heat, work, and energy in a macroscopic system, is characterized by 3 laws, and then after the third law, people looked back and realized that really there was another law that should have come first. Instead of renumbering them, they added the 0th law of the thermodynamics. Yes. It's silly, but we are going to start with the 0th law of thermodynamics. In today's lecture, we will talk about 0th and 1st law, and next time we will talk about 2nd law. The 3rd law is a technical and small addition. We won't really focus too much on it because its 2nd law contains the essence of the part of the story. Right. The 0th and 1st law are really about work and energy flow. So, the 0th and 1st laws are really about work and energy flow. The 2nd and 3rd laws are going to add a new concept which we are going to call entropy. It's a whole new topic, so we want to leave that until we need it. Today, I want to put together all of the idea of energy and see how adding just a little bit of new language can help us to make sense of a much more interesting system than we have been looking at before. Right. This study has gone for a long time, you can just imagine when you think about how practically useful it is to understand thermodynamics that people have must cared about this back thousands of years ago. You want to keep warm in the winter, you would love to be able to keep the ice from the winter into the summer. There are lots of applications of understanding thermodynamics. In the old days, people developed a theory, and the theory went by name by the caloric theory. The caloric theory was quite believable for a long time, and it has been disproved in the classical physics era. The caloric theory was discarded. It was a theory which said what does it mean to say something is hot and something else is cold? The caloric theory says that what it means is that the hot things has some stuff in it. The caloric is a fluid, a physical material fluid. Hot things have more of this fluid. Cold things have less of this fluid, and it's nice because then when you think about the pouring fluids, it's like a flowing heat. A hot object heating up a cold object. You could think of as a transfer of the mysterious fluid from one to the other. It's a nice idea. It meshes with intuition about the flow. It just turns out not to be correct. There are consequences of that model which are demonstrably false. Yeah, this is what history is, right? History of the science. The making hypothesis and prove it, and later it was disproved, falsified by other people, because it is not absolute truth. But it was truth in a certain time, and it was pretty much useful to make things forward, right? So the basis for the contemporary model came from a physicist named James Joule. We've talked about Joules before. We named the unit of the energy after Joule. 1 joule of energy measures a certain amount of either energy or, if you prefer, work done, force times distance. Large C, James Joule didn't invent this idea. Other people had thought about it and talked about it, and he was attributed most of the credit partly by the historical accent and partly because he was just well situated. He did some excellent, high-quality experiments. He defined them very well. He loaded up nicely. He was a part of the physics community, and so we think about James Joule as one of the originators of this idea that when we are thinking about the heat, we are really thinking about the flow of energy, and we are talking about thermal energy. We mentioned this before when I talked about energy. I said it comes in many forms. One form is kinetic energy. That was the first form we thought about. And the formula 1/2 mv square mass times the square of velocity tells you how much energy you have, how much energy was defined as how much work you could do, how big of the force you could apply over how long of the distance. That was one form of energy, and and then we talk about the gravitational potential energy and the chemical potential energy. We mentioned thermal energy. It's another form of energy. Think about book sliding across the table. It starts off with energy of motion, pure, measurable kinetic energy. It has a certain number of joules of energy. Then it grinds to a halt and it stops. So you ask where the energy went. It did not go into the gravitational potential energy. It doesn't go up, and it's not really stored in an obvious way. It's not stored like a compressed spring. You are not going to have it back if you let it sit there. There is nothing you can do to have the energy back in any obvious way. Has it disappeared from the universe? No, it's still there, and we call it thermal energy. Wow! Now that we have this atomic hypothesis, we understand exactly where it is. The friction, the force between the book and the table, started making atoms jiggle, molecules jiggle, and a little bit more rapidly. If they are jiggling more rapidly, they have more kinetic energy, but it's hidden from our eye because the book as a whole and the table as a whole have no overall kinetic energy. Right. We can't see the kinetic energy. It's random. One molecule is going one way, the other molecule is going another way, but they all have a little bit more energy each, and it all adds up. That's where the thermal energy is stored. It's stored in the random kinetic energy of molecules themselves. It's a quantitative. You can count that energy. Thermal energy is measured in a joule, just like any other kind of energy. Wow! When you do experiments, you are trying to figure out whether this is a true statement or not. Back in the 1700s, after Newton, people were arguing about whether it's a caloric or physical substance, or whether it's energy that we are talking about, which is not a physical substance. It's a property of physics objects. It's a very different kind of model about what we are talking about when we are talking about heat and temperature and so on. These experiments people did were much tougher than you might think. It's easy enough to heat a pot of water, but to keep careful track of how much energy you consumed and where it went turns out to take about 200 years of steady development. Isaac Newton strode a little bit about heat and thermodynamics himself, but it was really 200 years later in the 1800s when people were really beginning to make a concrete physical science of all of this to realize that there are patterns and regularities. It doesn't matter what material substance you have or what circumstance you have. If you are trying to measure, why is it so difficult? Well, think about how difficult it is to isolate a system thermally. When you buy a thermos bottle is designed to keep the coffee warm for a while to thermally isolate the hot coffee from the cool outside world, and that works for maybe a couple of hours, at which point the coffee is cooled back down again. The thermos is a relatively modern invention. It requires a good seals, vacuum, and high-tech materials. Back in the 1700s, it is difficult to thermally isolate objects in order to study their temperature as you add energy to them. It's difficult to measure temperature to high accuracy. Nowadays, we have a very small and precise thermometers, but if you slide a book across a table, even with a pretty good thermometer, you are going to have a hard time carefully measuring the change in the temperature of the book and of the table. If the thermometer is like it was back in the old days, some big, bulky object with a lot of fluids in it, then begin to interfere with the experiment that you are doing. You want it to measure thermal property of book, but you are mixing in the thermal properties of the thermometer itself. Wow! Of course, it's like a story of uncertainty principle, right? Of course, that's a very dangerous thing. You have to be very careful when doing physics not to be measuring the device that you are using to measure the physics. You want to measure the physics itself. Right.